Hi everybody, today we will be covering Unit 3, Lessons 4 through 6. Our goals for today are to explore relationships between two numerical variables. We want to find the best fit lines, and we want to look closely at different linear models. So the example we're going to start out with is called Aren't You Glad We're Boxing Fruit? So yes, oranges. We're going to start off with this video. And the video is of an individual putting oranges in a box. So we started out with 3 oranges. He's adding a 4th. He's adding a 5th. Make sure you take a look at how much it weighs each time he adds an orange. Okay, so he added 10 oranges. The first thing you might notice is that all of these oranges had different weights. That's because not every orange is the same. So I want you to take a second and go back and tell me how heavy it was when there was 5 oranges. And then tell me how heavy it was when there were 8 oranges. Okay, and if we were to go, we could pause our video and record each one of these. So at 3, it weighed 1, and then at 4, and then so on and so on. This would look something like this. It would be a table that included our numbers of oranges and how much it weighed with the box and the oranges. So normally when collecting data, we put this in a table. After we put it in a table, we put it in a scatter plot to help us see what's happening in that data. So at 3 oranges, it was 1.027. So it'd be somewhere here. At 4, it would be about 1.1. So it'd be a little bit higher. If we went all the way to 10, that was about 2.56. So we'd come in here, 2.56. And we would put them dot by dot. Let me show you what that would look like. It would look something like this. And then the next part we would do is we would draw a line through the data that best fits the data. So we call this our best fit line. Basically, it's a line that goes through your data that shows the trend that is happening. See, like this, it does not go through the data. So we would want to take this and move it down. Okay, so our best fit line might look something like this. However, we are humans, we make mistakes. So usually when we are doing statistics, it's best to do these things using technology. And luckily we have that readily available for us. So what we're going to do next is we're going to take all of these oranges and these information, we're going to put them into Desmos. Okay, so at 3 oranges, 1.027, 1.162, And then I'm going to go ahead and skip ahead and enter all of these. Okay, now that we have all of our points entered into our table, it plotted it for us, and now we can draw our best fit line. So we're going to take this green line and we are going to try to put it through our data. And if we zoom in, we want to try to go through as much data as possible, not having too many points above and not too many points below. So I'm going to move this down just a little bit. And honestly, we're just taking our best guess. So I would say that's pretty good. And then let's go ahead and take a look at our next question. So it says number 3, draw a line through the data. Okay, next we want to estimate a value for the slope of the line, and we want to see what that represents. Okay, so slope is how something increases, and each time we are adding oranges. So we want to see about how much the weight increases each time we add an orange. So at 4 oranges, it was at about 1.16. And then at 5 oranges, it estimated that it would be at about 1.4. Or sorry, at 5, it would be about 1.4. So we can see it increased a little bit more than 0.2. And then if we watch the next one, so at 5 on this line, this was at about 1.4, and then it went from 1.4 to 1.6. So each time it's increasing about 0.2 kilograms each time. Let's keep track of this number. So we would say our slope is about 0.2. And the thing about statistics is all of this varies. So this is just an estimate. And then it says, estimate the weight of a box containing 11 oranges. Will this actually be close? So let's go ahead and go back. We can zoom out a little bit. And we can either add 0.2 onto 10, or we can go to our line. So we want to estimate 11 oranges. So 11 would be about 2.73. kilograms. And then it says, would this actually be close? And so what do you guys think? If they were to add one more orange, do you think that's a good estimate based off of the trend? Yeah, I think that is a good estimate. They vary a little bit, but we already know how heavy it would be for 10, so only adding one more is not that big of a jump. Okay. Now it says estimate the weight for 50 oranges. Oh my goodness, 50, that's a lot. Okay. Let's come over here. We're going to zoom out. And we're going to go all the way to 50. So at about 50, this would weigh 11.41 kilograms. 11. Do you think this estimate would be close? Well, it might, but honestly, it's hard to say. We don't know what would happen after 50 oranges. Things might start changing. If we start putting a lot of big oranges, it might throw off our line. So since we don't know, we only know up to 10 oranges, 50 oranges is quite a big jump. We wouldn't really want to estimate that far. Okay, the next one says estimate the coordinates for the vertical intercept, and the vertical intercept, that's just your y-intercept. of the line that you drew, what might the y-coordinate for this represent? Okay, so they want us to go all the way back. And they want us to estimate our y-intercept. So our y-intercept is about 0.277. So if I have, let's write this down. So this is saying if I have 0 oranges in my box, it would weigh about 2.77 kilograms. So what would actually weigh 0.277? It's the box. Yeah, the box has to weigh something. So it's the box plus the weight of the oranges. And then it says, what points are the best fit in this linear model? Okay, let's go back. So we want to see which oranges fall on this green line. So based off of what you see here, let's make it a little bigger. Which oranges do you think best fit this line? I would say either 4 or 6 because those are exactly on our green line. Okay, and then it says which ones are the least fit for this linear model. Okay, so we want to see the ones that are the farthest away. So here's 3, we'll zoom in. 3, 4, 5, 6, 7, 8, 9, 10. So what do you guys think? I would probably say 5 because 5 is like all the way on top of the green, whereas the other ones are kind of close to it. But 5 is clearly off. And you can have multiple answers for that one. And then this says, how would the scatter plot and the linear model change if the box itself was heavier? So what would happen to this graph if my box weighed heavier? Well, it would no longer weigh 0.277, so it would actually shift the line up and it would take all of our points and move it up. My slope wouldn't change, just the y-intercept. Okay, can you think of reasons why the real weight of 50 oranges might be different from the answer we get by using the estimate? So like we said, maybe if the oranges from now on, they're all really big, it might skew our data. Since we measured 10 oranges, how does that affect your confidence in estimating the 50? I mean, we just don't have enough data, so I wouldn't go as far as 50. And then it says, how would the scatter plot and linear model change if grapefruits were used instead of oranges? Grapefruits are bigger than oranges, so what do you think that would do to our linear model? Yeah, we might have a different slope. We would have larger numbers, and so the graph would have a wider range. And then it says, in this case, there might be some meaning attached to the y-intercept. However, this is not always the case. Interpreting the y-intercept does not always make sense. So this one, it made sense. Like, hey, we're measuring the box and the oranges. Sometimes your y-intercept is just a little off due to normal data and everyday errors and stuff like that. You don't always have to look at your y-intercept, but you can sometimes. Okay, so the nice thing about statistics and all of these different technologies that we use is we estimated this best fit line just by looking at it, kind of hoping that it was somewhere in the middle. I think we did a pretty good job. However, there is technology that will tell you the exact best fit line. And in order to do that in Desmos, we would type in y sub 1 is about ax sub 1 plus b. If you type that into Desmos, it will write your best fit line. And what it told us is there's a slope of about 0.216, which we were good. We said ours was about 0.2 with a y-intercept of 0.345. And we said our y-intercept was about 0.277. So a little off, but not too bad. But that's the thing, like everyday life, everything you measure is going to be a little bit different. Nothing's ever the same. But our estimate was pretty good. Oh, and then why do we need to use technology to give us these exact numbers when we're collecting these data? Because we want to compare it to find out our residuals. So a residual might be a new word for you. It is the difference between your y value for a point and the predicted value. We had predicted this green line for the oranges, right? But you might have had some of the oranges above, some of the oranges below. So a residual is basically the difference between your estimated and your actual value. So how do we calculate it? We take our actual value and we subtract it by our estimated value. And that would tell us how much space, that's how much space we have between our predicted and our actual. So they want to know how close we got. Did we guess good? Did we not guess good? How was our data? So again, we have our weight in kilograms for these oranges. And we're going to compare them. So the actual weight of 3 oranges was 1.027. However, based off of our line, if we look for 3 oranges, zoom in, 3 oranges was about 0.9. So if we wanted to find our residual, we would take our actual and then subtract it. So let's get our calculator. And we would take 1.027 minus our 0.9. So our residual would be about 0.127. And then we could keep going over and over and over. What was our actual? What was our estimated? So this one was our green best fit line. And we would subtract them. So actual subtracted by our estimate. And that would give us about this. So that's, again, the nice thing about statistics is you can plug these numbers in and the program will calculate it for you. If your residual is a positive number, that means your actual was above your estimated line. If your residual is negative, that means it was below the line. So let's take a look. Do you see how this orange is above our line? That means the actual value was above the estimated. This would be a negative residual because it's below the line. This would be a positive residual. This would be, if you have a residual of 0, that means your actual was the same as your estimated. And then this is a graph of just residuals. So instead of having it compared next to that green fit line, they compare it to the x-axis. So we're going to pretend this is our estimated line, and then these are our residuals. So this estimated was a little bit high. This one, you see how far away they are? The closer to the line, the better. So the closer to the x-axis, the better. Because we want our residual to be 0. That means we did a good job and we estimated correctly. So let's try. This says each of these graphs are of residuals of the same data using different best fit lines. Which graph is most likely to represent the residuals from the best fit line? So which one of these is best? Maybe these are 3 different students. They each drew different lines. Who got the closest to being the best fit line? I would say A. So A has all of my points pretty close to my x-axis. These ones, this person, they overestimated, and look, all of these were below the line. These were all negative residuals. This one, oh, look, you have data over here. They kind of were a little off. They tried to get really close to these ones, but they left out these other points. Okay, so let's talk about slope. You have 4 different situations here. I want you to tell me the slope of this best fit line. So this best fit line is blue. What is the slope based off of this equation? The slope would be negative 9.25. What about for part B? What is my slope? Positive 0.44. Good. What is my slope for part C? A slope of 4. And what is my slope for part D? Negative 2.4. Very good. And then what about the y-intercept? If this line were to keep going and going and going and going, about where do you think it would intercept the y-axis? You actually could just look at the equation. So the y-intercept would be about 400. So if we were to continue this, it would cross at about 400. For this one, we would cross at about 0.04. Here we would cross at about 87. And where would we cross here? What's our y-intercept for D? 25. Very good. Should you always try to interpret the y-intercept? No, sometimes it's not important for your data that you're collecting. Okay, let's try another one. So this one says the scatter plot shows the maximum noise level when different numbers of people are in the stadium. The linear model is given by the equation y equals 1.5x plus 22.7, where the y represents the maximum noise level and the x represents the number of people in thousands at a stadium. So they gave us our dot plots, our scatter plot. They put our best fit line, and for that best fit line, they said it was y equals 1.5x plus 22.7. The slope of the linear model is 1.5. What does this mean in terms of the maximum noise level and the number of people? So what is my slope representing? What it means is for every 1,000 person, the noise level will increase 1.5 decibels. That's a lot. A sports announcer states that there are 65,000 fans in the stadium. Estimate the max noise level. Is this reasonable? So if we come over here, we want 65,000. So we would come up and estimate here. So what do you guys think is a good estimate? We could say somewhere between 115 and 120 decibels. Is that reasonable? Based off of the trend, yeah. Like most of the level is here. Some people are a little quieter, but more people causes the noise level to increase. Okay, it says, what is the Y-intercept given the linear model? So what's our Y-intercept for this one? 22.7. Is this estimate reasonable? So it's saying that there's 22.7 decibels of level before there's any people in the stadium. Is that reasonable? I mean, it could be. I don't know. Depends on what's going on. Maybe they have music playing. Fitting lines with technology. Yum, ice cream. Okay. This one says the weight of ice cream sold at a store in pounds and the average temperature outside are recorded in this table. For this data, create a scatter plot and sketch a line that fits the data well. So we want to take these points and we want to put them on a graph. So we're going to actually use technology again to help us because it's going to be more accurate than it would be if we were to try and graph it ourselves. Okay, let's go ahead and put this in Desmos. So we got 20 and 6. $18 and 4.5. Okay, now I have all of my points from this table in my graph. So again, they want us to put our best fit line. So we want it to go through these points. Let's zoom in. We want to do our best to try to have as little space above and below. See, like if I had this, all of my points would be above that line. That would not be a very good fit line. I want to try to go in between. Okay. And the way you can tell if it's good or not is we want to see how many points are above and below. We want to try to have an even amount. So I got 1, 2, 3, and I got 2 here. So maybe we can move this a little bit more. Okay, so now I have 3 on top and 3 on bottom. And we don't want these to be so far away from each other. So we're actually going to move this over. Okay, so that looks good. Okay, our next question said, for this data, create a scatter plot, sketch the best fit line, use technology, round any numbers to 2 decimal places. What are the values of the slope and the y-intercept for this best fit line? And then what do these mean? Okay, so first let's look for the y-intercept. Okay, what is my y-intercept? My y-intercept is negative 7.857. And these are degrees. Okay, so maybe we don't need that information because all of our data is up here. We probably are not going to get our ice cream out here when it's negative 7 degrees. Okay, let's try to find our slope of this line. So here at 18, it is about 4.8. When we go to 19, it is about 5.5. So we would do 4.8 and 5.5, and we would subtract those. We do 4.8 minus 5.5. So about 0.7. So our slope is about 0.7. Our slope is about 0.7, and our y-intercept was about negative 0.7. So if I wanted to write this as an equation, we would write y equals 0.7x minus 7.86. And then it's saying now, using this best fit line, predict the value when x is 10. Is this a good estimate? So let's go back to our data. They want us to predict 10. So all of our data is here. And if we come to 10, that would be about negative 0.82 degrees Celsius. Do you guys think that's a good estimate? It could be. I would probably say no, because that's just so cold. Okay, one last one. It says, what is a line of best fit? How do you know that you have a line of best fit? And which lines fit the data better? So your line of best fit is a line that goes through your data with not too many points above or below it. How do you know that you have the line of best fit? You can either use technology or you can count the amount of points that are above and below it. Check your residuals. Your residual will tell you if you have a good best fit line. So which line best fits this data? The solid line or the dotted line? What do you think? So the dotted line would probably fit it a little bit better. You can see the slope matches the trend a little bit more and the y-intercept matches it a little bit more. All right, so what was our goal for today? Our goal for today was to describe rate of change and y-intercept for linear model. I think you guys were able to do that because you're familiar with slope-intercept form already. I want to be able to draw my linear model. We were able to do that with the technology. And I want to be able to use the technology to find my best fit line. We can do that by adding a certain formula into Desmos. And then lastly, I want to be able to plot and calculate my residuals. So remember to calculate your residuals. You take your actual value and you subtract it from your estimated value. All right, I hope you guys have a great day. Let me know if you guys have any questions, and I will see you guys later.